Welcome to The Explainer. Today, we're diving straight into Chapter 18, Soil Exploration. Imagine slapping down a massive multi-million-dollar structure on a patch of Earth you haven't actually checked out. If we don't know exactly what's going on beneath our feet, even the most brilliantly engineered superstructure is frankly doomed to some nasty surprises. Let's look at why this is an absolute deal-breaker.
Think about this number for a second. A thorough soil exploration program usually eats up less than 1% of a project's total budget. Literally just 1%. It's a tiny, almost microscopic price to pay to avoid, catastrophic foundation failures, insane cost overruns, and structural distress down the line. Honestly, skipping or underfunding this step, it's one of the most dangerous gambles you can make in engineering.
Okay, let's dive into this by clearing up two terms that get tossed around interchangeably, but actually mean very different things. Site investigation is the broad stroke. It's the big picture, checking out the surface, assessing the general subsurface conditions, looking at maps, aerial photos, walking the site. Soil exploration, on the other hand, is the surgical strike. It falls under that broader umbrella, sure, but it focuses strictly on the nitty-gritty field and lab work needed to get precise engineering properties of the soil.
So, what exactly is the endgame here? You can think of it as a high-stakes diagnostic mission. We have a few primary objectives. We absolutely have to map out the exact sequence and depth of the soil strata. We need to locate the groundwater table and, critically, see how it fluctuates. We've got to extract actual physical samples of the Earth. And finally, we need to pin down those vital in-situ engineering properties, like strength and compressibility, because those numbers literally dictate how our structure is going to perform. Now, to get this data, we usually start simple. You can think of reconnaissance and test pits as the Earth's initial physical exam. These are open, accessible trenches, and they're fantastic because they let us visually inspect the soil right there in its natural state. You can just carve out blocks for the lab. But, and it's a big but, they have a strict limit. They're only really practical up to about 3 meters deep. Go any deeper, and costs absolutely skyrocket because suddenly you're battling incoming groundwater and building massive lateral bracing just to stop the walls from caving in on you. So, when we have to go deeper than a standard pit, we turn to boring. And we've got quite the arsenal here. Auger boring is great for soils that hold their own shape. Percussion drilling? That drops a heavy churn bit to literally smash through stiff soil and rock. Rotary drilling is the gold standard for pulling up rock cores. But wash boring is where it gets really interesting. We pump water down the drill rods to wash the soil cuttings up to the surface. It's mostly just to dig the hole quickly, but a sharp engineer is watching that return water like a hawk. A sudden shift in the color of the wash water, or the drill suddenly speeding up or slowing down, boom, that instantly tells you that you've just punched into a totally different underground stratum. It's fascinating how the scale and type of the project completely dictate the strategy. The required distance between your boreholes totally depends on what you're building. If it's an earth dam where seepage and massive loads are life or death, you're dropping a hole every 30 to 60 meters. Building a multi-story tower with heavy, concentrated column loads, you tighten that up to every 15 to 30 meters. But for a highway survey, where the load is spread out over miles and miles of pavement, you can space those borings way out, anywhere from 300 to 600 meters apart.
Of course, deciding how far apart to drill is only half the battle, right? We also have to know how deep to go. The Indian Standard Code gives us a great rule of thumb here. Normally, explore down to 1.5 times the width of the footing measured from below the foundation level. Why? Because if you have multiple loaded areas close together, their stresses overlap deep underground, and you need to know what's down there to handle it. But get this, nature throws curveballs. Fast-growing, water-seeking trees can actually alter the soil's weathering processes way deep down, which forces engineers to drill well beyond those standard calculations just to be safe.
Let's shift gears for a second. Sometimes you need to map a site, but you don't want to drill 100 holes. Enter geophysical methods. Honestly, you can think of these like the Earth's MRI or X-ray machines. They're indirect, totally non-invasive, and they let us evaluate massive areas rapidly. We can literally map the boundaries between different underground materials without ever putting a single shovel in the dirt. The two heavyweights in this space are seismic refraction and electrical resistivity. Seismic refraction sends shock waves into the Earth and times them because, as you know, waves travel way faster through dense rock than loose dirt. Electrical resistivity takes a different route, measuring how much the soil resists an electrical current. It's awesome for finding groundwater or ore. But listen, there is a massive blind spot here with seismic testing. It completely fails if a hard, dense rock layer sits directly on top of a soft clay layer.
The shockwaves just speed along that hard top layer and completely mask the soft, potentially dangerous foundation soil hiding underneath. Sneaky, right?
Now, when seismic refraction does work, we plot the data out to find the hidden layers. It's essentially mapping distance versus time. What we're looking for is the exact moment the slope of the line changes. That precise kink in the plot? Mathematically, that's the golden ticket. It reveals exactly how deep the next layer is and how dense it is.
But look, whether we're using wash boring, test pits, or shooting shock waves into the ground, the ultimate goal of all this exploration is almost always to find the right spot for a soil sample. This is the Earth biopsy. At the end of the day, we have to physically extract a piece of the Earth, haul it up, take it to a lab, and put it under intense physical stress.
When we do pull that dirt up, it's going to be either disturbed or undisturbed. A disturbed sample has had its natural structure totally scrambled by the drill. Great for basic classification, absolutely terrible for strength testing. An undisturbed sample aims to keep the soil's natural matrix perfectly intact. So, the crucial point is, a truly 100% undisturbed sample, it's basically impossible. Just pulling it out of the ground releases the confining pressure. So engineers just get as close as physically possible using specialized thin-walled samplers, and they tightly control a metric called the area ratio to minimize displacement as the tube slices into the soil.
Sometimes, though, lab tests just don't cut it. We need to know how the soil acts right there in the ground. That's where penetration tests save the day. We drive a standard device, maybe a hollow tube for the standard penetration test, or a solid cone for cone penetration tests, deep into the subsoil. By counting the exact mechanical energy it takes to punch that penetrometer down, we get critical in situ data. Things like the standard penetration number, which directly ties back to the density and bearing capacity of the soil right where it sits. Okay, zooming back out to the macro level. All of this intense work, the test pits, the shock waves, the delicate sampling, the penetration driving, it all culminates in one epic document, the Soil Investigation Report. This is where the whole underground mystery is finally solved. The report synthesizes every single data point into a comprehensive subsurface profile, and it makes the final, definitive call on exactly what type of foundation can safely hold our structure up.
Now, what's really interesting is the tangible output of all that fieldwork, the boring log. It's literally a map of the underground world at a specific spot. It tracks the exact depth, the thickness of each stratum, and the soil classification, like SP for poorly graded sand. It even logs exactly where the undisturbed samples were pulled and marks the crucial groundwater level. When engineers lay a bunch of these logs side by side across a site plan, they can literally see the layers of the earth rising and dipping beneath the surface. It's like having X-ray vision.
But here is the wild reality of geotechnical engineering that keeps everyone on their toes. Even with all these borings and tests and detailed logs, we still only have concrete data for the exact vertical columns of earth we drilled through. We have to mathematically guess or interpolate what happens in the massive gaps between those boreholes. And yeah, connecting the dots is an educated, highly scientific process, but it's still a high-stakes guess. So, are we ever truly 100% certain of what lies beneath our feet? The Earth is complex, chaotic, and always changing, which is exactly why thorough soil exploration isn't just a regulatory checkbox, it's an absolute engineering marvel.